we have a thermodynamic system where we have a cylinder, piston, and stuff like that. We have the area, pressure is P, and the height is h. If the piston is displaced a little bit, it has a piston as a mass m, find the time period of oscillations and we have to assume isothermal conditions. Okay, so let's do this. Let's quickly make a drawing. We have our cylinder over here. This is our piston. Inside we have gas. So let's put gas. Our gas is going to be red color. And that gas has some pressure. As of now, that pressure is P. This height is h. The mass of this piston is m. And we're going to display, and right now it's in equilibrium, it has to be, and isothermal conditions, so there must be a thermal reservoir over here maintaining the temperature and everything. So it doesn't matter, we're just going to assume isothermal conditions, and we're going to push this down a little bit and figure out what's going to happen. Okay, so let's try and understand what's the current situation. The current situation is in equilibrium, so right now on that piston, so here is our piston, mass m, there are two forces acting. There is gravitational force, that is mg. You could also say there is a force due to atmosphere acting from the top, but you will see that doesn't matter. Even gravity for that matter doesn't matter actually, as you will see now. Anyways, let's forget about that force, or if you want, fine, let's include that force also. There's a force due to atmosphere. Let's make it accurate. So the atmosphere is pushing down on this particular piston. So there is an atmospheric force, and that force is going to be the atmospheric pressure, that's P naught, times A. So these two forces are pushing it down, and since the piston is in equilibrium, there must be a force upwards. And that force is put by the gas. And the gas must put a force pressure times the area. That's the current pressure, that's the current area. And since this is in equilibrium, these two must cancel each other out. So PA, we know right now, is mg plus P naught. Okay, now what I'm going to do is I'm going to displace this guy a little bit downwards. So he's going to end up coming here somewhere, and let's call this displacement as y, and let's consider downwards as positive because I like the direction of displacement to be positive. Okay, the moment you push this down, we have decreased the volume, so pressure will increase, and since the pressure increases, the upward force increases. These two forces pretty much remain the same, they're not going to change. So the pressure increases, so there's an additional force, and that additional force is going to accelerate this piston upwards. And we need to calculate what that additional force is. To calculate that additional force, we need to calculate what is the change in pressure. So to do that, we're going to use the isothermal conditions which are given to us. We are given that isothermal conditions, PV is a constant. So let's build a differential equation for this. We can say that what can we say? Alright, so we can say dP times V plus P times dV must be equal to 0. Just differentiate this guy. dP is the change in pressure which I am interested in. So dP becomes minus P dV divided by V. The minus V is already telling me that the volume dV is negative, so I already have taken care of all the negative signs. Alright, so dP now has to be equal to minus P, that's the current pressure, times dV, that's the change in volume. And since this displacement is extremely small, we can use dV and calculate what that change in volume is. That change in volume has to be this number, this area which we have taken, right? So that, not that area, that volume. And that volume is the area of the piston that was given to us. I forgot to mention that in the drawing. So here is the area of the piston multiplied by y. That's the change in volume. So the change in volume is just A times y. A times y divided by the actual volume, the current volume, I mean the volume before. And the volume before is A times h. Therefore, the change in the pressure, it's the extra pressure, is going to be minus P times y divided by h. Okay. So what's going to be the additional force the additional force, dF, the extra force that's going to come on this, is going to be dP times A. So that's going to be minus PAY times H. That's the additional force, okay? The minus sign is indicating it's in the upward direction, so everything makes sense now. So let's redraw the situation now. What are the forces acting right now? We still have the gravitational and the atmospheric pressure. That's not going to change, plus P naught A. But now the upward force has changed. Initially the upward force was PA, but now we have an additional force. And the minus sign is already telling it's upward, so if I put the magnitude, the additional force is going to be this dF. And that is that PAY divided by H. Notice, it's this additional force that's the net force now, because these two are just cancelling each other out. And that's why I told you that it really doesn't matter whether they put this into the picture or not. This guy is going to cancel out with this guy. So the net force is only PAY divided by H, okay, in the upward direction. So let's build a differential equation now. Okay, net force must be equals to mass times acceleration. And the net force is minus, because it's upwards, when I put the differential equation, I need to take care of my signs. It's minus PAY divided by H, P by H, equal to mass times A is d square y by dt square. That's the acceleration. Notice that I'm building the differential equation. By now this must have become boring. Now it's no more an excitement, because we know how to work with these differential equations now. It's plus PA divided by H into y equal to 0, and I bring it in the glorious form now. D square y by dt square plus PAY divided by m times H times y should be equal to 0. And notice, I'm not going to even say it. I'm pretty sure you got this by now. And therefore, this guy over here must represent the angular frequency. Okay, so omega square must be equal to PA divided by mH. And what are we asked to calculate? Find the time period. Alright, so time period is going to be 2 pi square root of mH divided by PA. Ta-da! There we